Hello everyone, I'm Cui Ziyu from University of Chinese Academy of Sciences. It's my honor to be here and talk about our work, differentially testing database transactions for fun and profit. Database management systems like MySQL and PostgreSQL and so on play an essential role for storing and retrieving data in many applications, such as e-commerce applications. For convenience, we call database management systems as DBMS. DBMS need to ensure data consistency and integrity. For example, a user Alice wants to transfer money to Bob. In general, there are two steps by database standard language, structured query language. First, database subtracts $100 from Alice's account, then adds $100 to Bob's account. We don't want any of these steps to go wrong. DBMS utilize transactions to ensure data consistency and integrity. With structured query language, transaction is started by a start statement, such as begin statement, and finally transaction is committed by commit statement to ensure that the two manipulation statements are executed as a whole. DBMS provides several common isolation levels to balance consistency and performance, such as read uncommitted, read committed, repeatable read, and serializable in MySQL. However, transaction bugs can occur due to buggy transaction implementations, which cause incorrect database states and query results. For example, a user wants to check the balance before the transfer. Two transactions perform these operations concurrently on Alice's account. First, transaction 1 and transaction 2 query the balance. They both see that Alice has no balance. So transaction 1 adds $50 to Alice's account, and transaction 2 concurrently adds $100 to Alice's account. So Alice's balance should be $150. However, after two transactions complete, Alice's balance is $100. That is, update in transaction 1 is overwritten. In fact, such bugs cannot occur in DBMS today. So we show a simplified real-world transaction bug in MariaDB, which is detected by our tool. The initial table contains one primary key column with the record 3. Transaction 1 first updates the record to value 5. Transaction 2 concurrently tries to delete all data and is blocked. Then transaction 1 inserts a value 2. However, MariaDB encounters a conflict at this insert statement, resulting in a deadlock that occurs in transaction 2. In this case, transaction 2 is rolled back. Transaction 1 then is committed. Transaction 2 then inserts a value 1 and executes rollback statement. We finally retrieve the table and observe that the results in MySQL and MariaDB are different. As expected, the database state in MySQL contains records 1, 2, and 5, while that in MariaDB contains records 2 and 5 due to unexpected rollback. Many approaches for automatical DBMS bug detection have been proposed. Some works construct Oracle for single select queries to detect DBMS logic bugs, such as Circle-Smith and TRP. These works can also detect crash bugs in DBMS. Some works utilize differential testing, such as Rex and Apollo. They compare query results among DBMS to detect bugs. However, these approaches are designed to find specific DBMS bugs and cannot detect transaction bugs. To improve the correctness of transaction implementations, existing works mainly focus on verifying whether DBMS provide the transaction isolation guarantees that they claim. For example, Eddy and Cobra utilize simplified database structure key value model, analyze the transaction history and dependency graph to find transaction bugs. However, they cannot detect transaction bugs that use complex data models, such as database constraints and cross-table queries. Our key observation is that transaction execution behaviors should be the same at the same isolation level in compatible DBMS. Inspired by the observation, we propose DT-square, a general transaction testing approach leveraging differential testing for automatically testing transaction implementations in DBMS. Here is the overview of TT-square. First, TT-square randomly generates transaction and a submitted order as test case. Then TT-square submits the transaction statements in the submitted order one by one to each DBMS for execution. Finally, TT-square compares the execution results of different DBMS at the same isolation level. If the execution results are different, TT-square generates a test report. We manually analyze whether it is a bug. If not, the test case is classified as a compatibility. First, TT-square randomly generates data type, data, and constraint for initial database, and randomly generates circle statements based on circle syntax supported by tested DBMS. Since circle statements usually require some parameters, TT-square randomly selects some generated tables and columns to populate the statement parameters. TT-square explicitly starts a transaction using a begin statement and randomly ends it with a commit statement to apply all changes, or a rollback statement to roll back all changes in the transaction. Circle statements types in transactions include select, update, insert, and so on. A technical issue for transaction differential testing is non-determinism transaction execution. Given a group of concurrent transactions, their execution will be affected by non-deterministic schedule. Therefore, the execution orders of the statements in transactions, which are part of the testing inputs, need to be unified. The submitted order indicates the initial order in which a DBMS accepts statements in concurrent transactions. Concurrent transactions should not violate their isolation level in any execution order. Thus, we can enumerate all submitted orders for a group of transactions. To address the issue, we propose a deterministic transaction test protocol. We submit transaction statements in our generated transaction test case to a DBMS one by one in a randomly generated submit order. For each submitted statement, we set up an individual thread to execute. If a statement is successfully executed, we record its execution result and add it into the execution order. If a statement is a select statement, we record its query result. If a statement does not return its result within 2 seconds, we determine that the statement is blocked, and mark it and its transaction as blocked, and place this block point in the execution order. We then skip the block statement and its following statements that are in the same transaction, and execute other unblocked transactions. A commit statement resumes other blocked transactions. Then we obtain these resumed transactions, mark them as unblocked, and fetch their corresponding block statements' execution results. Then we scan the submitted order from the beginning and pass the unsubmitted statements to the DBMS. After all transactions complete, we retrieve the database state and store it in the execution result. TT-square executes a group of transactions for each DBMS under a certain submitted order following the test protocol, and compares their execution results to find discrepancies. TT-square compares the execution results for each statement in the execution order from beginning to end on 2 DBMS. Once TT-square finds a discrepancy, it will not continue to compare the following statements. For example, for 2 statements, if one of them is a blocking point, while the other is not, TT-square reports a discrepancy with inconsistent blocking. For query statements, if their query results are different, TT-square reports inconsistent query result. If a transaction test case triggers a discrepancy, we investigate whether it is a bug or a compatibility issue. For each detected discrepancy, we first investigate the transaction implementations from development documents provided by related DBMS to analyze whether a discrepancy is specified by the document. If the answer is yes, we classify it as a compatibility issue. Once we find that the discrepancy is not specified by the document, we report it to developers as a potential bug. If developers confirm that the discrepancy is a compatibility issue, we will reclassify it as a compatibility issue. Otherwise, we will reclassify it as a bug. To demonstrate the effectiveness of DT-square, we evaluated on three widely used MyCircle-compatible DBMS: MyCircle, MariaDB, and TiDB. MyCircle and MariaDB support 4 isolation levels, that is, read uncommitted, read committed, repeatable read, and serializable, while TiDB supports read committed and repeatable read. DT-square has detected 16 unique bugs, among which 6 bugs have been verified as previously unknown bugs, and 6 bugs are duplicate. We show a simplified test case that triggers a new transaction bug in MariaDB at all isolation levels detected by DT-square. The initial table has one primary key column with record 3. Transaction 1 first updates value to 2, while transaction 2 simultaneously deletes all rows and is blocked. Transaction 1 then updates value and is committed. After that, transaction 2 is resumed and queries the database state. After transaction 2 is committed, the database states of MariaDB and TiDB are different. As expected, TiDB returns the empty table due to the delete operation in transaction 2. However, MariaDB returns value 1, so DT-square detects this inconsistent database state. The root cause of this bug is that MariaDB does not update primary keys atomically. This bug will be fixed in the upcoming release version. DT-square has also detected 92 unique compatibility issues, including 88 transaction-related and 4 transaction-unrelated compatibility issues. We mainly study these 88 transaction-related compatibility issues. From these transaction-related compatibility issues, we identify 3 root causes, that is, inconsistent lock mechanisms, inconsistent snapshot creation, and the aborted transaction is different when a deadlock occurs. Most compatibility issues are due to inconsistent lock mechanisms. Here is an example of repeatable read for MyCircle and TiDB. The initial table contains only one row with record 2 and null. Transaction 1 first updates 2 columns value to 1, and transaction 2 tries to update the row where column C2 is not null. In TiDB, transaction 2 first evaluates the where condition on the first row to be false, so it is not blocked. However, in MyCircle, transaction 2 is blocked. Then transaction 1 is committed. In MyCircle, transaction 2 is resumed and updates the row successfully. So this compatibility issue is caused by inconsistent log mechanisms in 2 DBMS, which affect their execution order of transactions, as shown in red arrows. 6 compatibility issues are caused by inconsistent snapshot creation location at repeatable read. Here is an example for MyCircle and TiDB. The initial table contains one row with record 1, 1. Transaction 1 first starts, then transaction 2 starts, deletes the row where column C1 is 1, and is committed. Finally, transaction 1 retrieves the database with select statement. TiDB returns the result 1, 1, whereas MyCircle returns an empty set. Because TiDB reads the snapshot established in the begin statement in transaction 1, MyCircle reads the snapshot created by the first select statement. After transaction 2 is committed, the database states are consistent, that is, an empty set. So this compatibility issue is caused by inconsistent snapshot in 2 DBMS, which affects their query results in transactions. As a result, compatibility issues among compatible DBMS are common, although isolation levels have been clearly specified in literatures. Transaction execution behaviors can be seriously affected by various design choices in different DBMS, such as log mechanisms and snapshot creation. Transaction specification can alleviate these compatibility issues. For the 88 transaction-related compatibility issues, 66 can cause inconveniences among DBMS, that is, inconsistent database states and query results. The remaining 22 issues can cause inconsistent block statements, but do not affect the final execution results. Therefore, DBMS application developers should be aware of these compatibility issues when migrating their applications among DBMS. In conclusion, We propose a differential testing approach for transaction to detect transaction discrepancies among database management systems. The evaluation on real-world DBMS shows that our tool D-Square is effective. Our tool and data can be found in GitHub. That's all. Thank you.